Okay, so good morning, everyone. My name is Tim Vanderlyn. I'm a research scientist at CSIRO Manufacturing, and I'm here representing the Australian Institute of Physics in this co-branded seminar between the Australian Institute of Physics and the Centre of Excellence for Quantum Computation and Communication Technologies. The first order of business is to acknowledge the traditional owners on the lands that we're all meeting on today. I'd like to pay my respects to the Teramagal and the Camaragal people who are the traditional owners of land that I'm on today. And I'd like to extend a welcome to any Aboriginal or Torres Strait Islander people um, that, that are here today. And I guess without much further ado, I'd like to introduce the speaker for today, who is Dr. Aaron Taranto. Aaron's going to be given a presentation based on machine learning in quantum technology. A little bit of a background for Aaron. Aaron is a postdoctoral researcher in the Department of Quantum Science Technology at the Australian National University. Aaron's research is based on cold atoms and quantum memory platforms, engineering atom-flight interactions, and specifically about applying machine learning to these systems to solve really cool quantum physics problems. So I'll hand you over to Aaron now.
Thanks, Tim. Hello, everyone. Thanks for coming today. So as Tim mentioned, the talk that I'm going to be giving today is on machine learning for quantum technology. So this is some research that we've been doing over the last 4 to 5 years. I started this research during my PhD, and then I've sort of carried it on into my postdoc, which I'm doing at the ANU as part of the ANU Quantum Optics Group. So I've sort of divided this talk into 3 parts, being a little bit cognizant that not everyone here necessarily has a background in machine learning or even necessarily physics. So I'm going to keep it kind of general and hopefully just get across some of the main ideas that people might need to know to understand exactly what it is we're doing and why I think it's super cool. So the first part, I'll just talk about machine learning and neural networks, give a sort of brief background and overview into what they are, how they work, and why they're useful. In the second part, I'll talk about some work that we did building on these deep learning platforms, which is a deep learning optimizer, and how we applied that to our quantum memory system. And the final thing I'll talk about is some other deep learning applications, which are the sort of future prospects and what we're doing at the moment. So the first part is machine learning neural networks. So one of the big questions is, what is machine learning? And it's a pretty good question. Anytime anyone brings up machine learning, it sounds like this sort of black magic method that anyone can use and get all these crazy results. But really it's just a process. And so the idea of machine learning is to distill an algorithmic approach that can solve a particular problem using computational means. So what does that really mean? Well, it means we want to take tasks that are maybe difficult for humans and try and actually figure out how to do them. Sometimes these tasks can actually be easy for humans as well and difficult for machines, and we still employ machine learning because it's an easier way of doing things. So to give it a brief example of that, the question becomes, why learn? And what is learning anyway? Like, we're all familiar with creating mathematical models to some degree, even really basic ones. If you're doing your taxes, that kind of stuff, you have these relationships between various finances. But why would you bother doing something that's more complicated than that? Well, let's assume that I want to do a particular task. And in this case, my task is actually going to be to create a model that takes images and determines whether there's a dog inside that image or not. So I'm going to create my model. I'll call it my dog finder. And so it's pretty simple. I pass in my dog, and it tells me, yes, there's a dog in here with some probability of success. So the way I would normally try to construct a model like this is I would start by creating a model, and I lay out some sort of criteria, right? So here my criteria for a dog is 4 legs and a tail, and that, if I can find some stuff like that in images, then I'm doing pretty well about describing dogs. But then the problem arises that there's going to be a few different cases where the criteria that I've laid out actually covers different things. So I have a cow now, and I put that in my dog finder, and it's like, well, you only asked me to find things that have 4 legs and a tail, so that's kind of like a dog. Okay, well that's fair. That is what I asked you to do. So I'll add some additional criteria. I'll say, well, no horns. No horns for dogs. Okay. Well, now I guess this is technically also a dog. I mean, it looks kind of like a dog. It satisfies most of the criteria. And if I put that in my dog finder, it probably tells me it's also a dog. And so this raises an interesting question, which is it's very easy for you and I to identify what a dog is. You know, we can very quickly be like, well, that's obviously not a dog. That's just a balloon dog. But for a machine, that's kind of tricky, and actually building what this model would be referred to as a feature classifier, that's actually kind of a tricky task. So the idea is that with machine learning, we can solve problems that are hard for computers, but easy for people. And the idea that we want to try and use is to actually learn representations from the data. So instead, what I'm going to do is I'm going to get a large repository of images of dogs and then use that to train my model instead. So we're familiar with machine learning popping up in lots of different areas. We see the various applications already out there in the world, things like healthcare, so people have talked about using it for things like cancer identification, treatment prediction, drug design. You'll find it in the data security industries, things like fraud detection and smart intrusion detection, being able to figure out if people are up to naughty things. Financial trading, you can use it to do predictive trading and also trend classification. Natural language processing is a big name for something that people are probably familiar with. If you've ever opened up a virtual assistant app like Siri, then you've been able to talk to it with what's known as natural inputs, right? I don't have to give it specific commands, but if I open up an app and I say something like, hey, can you schedule a meeting for 2 p.m. on Friday? There's a lot of contextual information in that sentence that is actually kind of hard to get out, and that's what natural language processing does. And finally, there's things like automated systems, so for example, manufacturing, robotics, and all those good fun things. So there are effectively three types of machine learning that people generally classify machine learning as. And I'll just go over these briefly. So the first one that most people are familiar with is supervised learning. And that is the sort of example that I gave before, where I basically have a set of input data, which I'm going to feed into my model, and that will generate a prediction. So in the previous case, my input data was an image of a dog, and my model should tell me if it's a dog or not with some accuracy. So the way I train this is I already have predetermined labels, which is dog, not dog, etc. And I can work out whether it actually predicted this correctly, and I feed that error back to the model. Another type of machine learning is called unsupervised learning. This is a little bit harder to sort of grasp conceptually, but the idea is, well, instead of creating labels, I'm just going to let the model figure out what labels it should be. So if I start up with some data that has some structures and I let it go through a process, for example, something like cluster discovery, then I actually let it figure out where the data should be mapped to. And so these colored areas now represent my labels. And that's good for things where I don't necessarily know what the structure of the data is. So an example of this might be I give my model a lot of images of things that are kind of like dogs. So maybe I'll get some dogs, some hyenas, some lions, and I don't tell the machine learner what those images correspond to, but I just go and let it figure out what the differences are. And then maybe when I go back and look at the clusters later on, I'm like, okay, it's figured out that this little area corresponds to pictures of lions, for example. The final type of machine learning is reinforcement learning. And so the idea of this is a little bit different to the previous models, but basically you have some system that you want to interact with. And you interact with the system by getting outputs which correspond to the current state of the system and a reward. I then feed these things to my model, which is going to determine the best way to interact with that system. So this is kind of like a control problem. An easy way to think about that might be, I've drawn a little pendulum here, but we've all played that game when we were kids. You have a rake or a shovel or a stick and you walk around with it balancing on your hand and you're just trying to try and move your hand so it stays perfectly upright. That's an example, right? So I can parameterize that as the angle of my stick with respect to my hand. So I'm doing really well if it's vertical and stationary. And then my reward is like how long I manage to keep that stick up. And so I do all these actions, which is moving my hand around to try and figure out the best way to actually control the system. And it turns out you can do that with machine learning if you use this reinforcement type model. So just to try and decouple some of the terms, people often talk about artificial intelligence and how that fits into the scheme of things. So artificial intelligence in general, and I'm going to be quite general in this context, is really anything, really classifies anything that can mimic intelligence, right? So that can be something as simple as a chatbot that you've all used before, presumably if you've been on hold with Telstra for 20 hours. Um, but a subset of this is actually machine learning, right? And the idea of machine learning, as I mentioned before briefly, is this sort of algorithmic learning approach. So actually learning relationships from the data in some kind of data-driven way usually. Now, there's another subset of this, which is actually quite interesting, which is referred to as deep learning. And I've labeled this as black box structures because basically what they are these sort of magical models that people tend to throw at things and then they find all kinds of interesting results. And in fact, this is going to be the main thing that I focus on today. I'm going to try and hopefully impart the idea that deep learning is actually a really powerful tool to be used in a scientific context and also a number of different contexts. So what is deep learning? That's a very good question. It's a little bit complicated, but the general idea is that it is an attempt to emulate the neurological structures in biological entities. So what do I mean by that? Well, if you think about how your brain works, right? There is a lot of complicated information processing going on. So if someone goes to throw a ball to me, there is a lot of information processing that has to happen. My eyes, first of all, take this image, work out that there's an object coming towards me, also processing that someone has thrown an object at this time. I then have to sort of predict the trajectory that this ball is now coming at me. I then have to engage my muscles to actually go and catch this ball. And all of this happens, in tenths of a second. So there's obviously some really powerful computing structures going on in the brain, and I will say I'm not a biologist, so a lot of that explanation is probably maybe wrong, but it suffices. And so the idea of deep learning is to actually try and emulate this model of computing. Right, so I've got an image on the right hand side here, which is of a actual biological neuron. And so you have this sort of neuron with a nucleus and dendrites, which then connect to other neurons via these axon terminals, right? And so what happens is the model of computing that your brain uses is that as electrical impulses build up across this potential barrier here, eventually it'll cause this neuron to also fire, which is connected to other neurons. And if I have lots and lots of these neurons connected together, I can actually get some sort of information processing scheme going. Now, the good thing about deep learning is that it's very good at complex representations. And I'll make a bit of a case for that later. But, as you could probably imagine, that if your brain is good at representing complex tasks, then a model that tries to emulate that is also going to be good at it. And finally, deep learning is powerful. It has demonstrable success at a number of different tasks which were thought to be computationally intractable up until the last 10 to 15 years. Things like voice synthesis and deepfakes, which we've probably all seen, object detection, anytime you've seen self-driving cars using cameras to figure out what's going on, as well as text generation from writing prompts. So I'd like to show a few examples of these powerful models because I just think they're super cool, and if you've never seen them before, they're a little bit mind-blowing. So this first example is actually using a model which is called a generative adversarial network. Now, this is a fairly standard picture. You can see some people here. But the super interesting thing about this is none of these people exist. These these are basically faces that are never seen before, and they are generated entirely by a deep learning model. Right, and so the way this works is a little bit complicated. Basically, you're taking these models which have some input, which corresponds to a noise, and it maps to some output, which is a target space that you basically want to be mapping to, which in this case is faces. Now, it's pretty good. You look at this for the first time, you're like, wow, those are some nice looking faces. There are a few bits that look a bit funny, and you maybe can't quite tell. Until someone points it out. So let's actually have a look at one of those. Let's zoom in here. I don't know about you, but I usually prefer my teeth to line up with my nose, or just generally the center of my face. That's usually better. So these models, they do have some quirks. I'm told that later generations of this model actually fix this problem, but it's an interesting exercise in that deep learning can get most of the details right, but sometimes there's just some subtleties that it doesn't quite understand why that doesn't make sense. I guess in all of the training images, most of people's teeth were actually facing the front. So another interesting application of deep learning that I think is super cool is something called zero-shot voice emulation. So I think the most powerful way to show this is actually just to show the results itself. So if I take a 5-second sample of a voice, and this is going to be my 5-second sample, I'll play that for you now.
The Norsemen considered the rainbow as a bridge over which the gods passed from Earth to their home in the sky.
Then using this zero-shot learning approach, I can actually generate arbitrary speech using text and using this voice as a sample. So all of these following voice files are actually generated using this zero-shot approach.
His motives were more pragmatic and political. There were many editions of these works still being used in the 19th century. This work reflects a quest for lost identity, a recuperation of an unknown past.
Now, I think this is one of the craziest applications of deep learning. The fact that you can emulate a voice from only 5 seconds. Now, the way that this works is a little bit complicated. In a nutshell of how zero-shot learning works in general, the idea is that if I can create a model that, for example, knows about particular things. So let's say I have a model that knows that if I give it this picture, that it's a horse, right? Well, then I can actually extend that model in some fancy ways to try and predict outside of things that it hasn't seen before by knowing the sort of relationships between things. And what do I mean by that? Well, let's say I take my horse and then I add an additional attribute, which might be stripes. Now, if I describe to you a stripy horse, you're probably going to think a zebra, right? And that's the idea here. So it's taking these attributes so that these models can predict outside of this space to predict something that's interesting that they haven't seen before, but they should be able to generalize this information to know about. Now, this is a little bit of a tenuous link to the voice emulation, but suffice to say that, you know, these kind of models are quite complicated and we just don't have time to go over them. So extending the idea of deep learning, let's talk about how we actually build these things. So the building blocks of deep learning are these things called single neurons, and we're going to use single neurons to build up artificial neural networks. So a single neuron basically just looks like this transform here. I have a bunch of inputs with a set of weights connected to some neuron. I got a bias term, which basically just gives me an offset, and then I have an activation function. Now this activation function is actually the most sort of important thing here. This is a nonlinear function that tries to emulate the firing behavior of neurons. So for the first time I send in these inputs, if I have enough weights on these inputs and these inputs are, say, bright enough, then, or large enough might be a better word, then what that means is that this activation function is actually going to fire at some point. And if that is connected to other neurons in my network, well then I can institute a model for computing. So taking that a bit further, let's talk about what a single layer looks like. So here I just have a single layer with 2 neurons, which, you know, is not particularly powerful, but you can see that if I just start adding these things together, and I've chosen tan hyperbolic here to be my activation function, and so this is what the activation function actually looks like. You can see it basically does nothing until some point and then it turns on. Then even with just 2 neurons, I can start to represent complicated functions, for example, like a Gaussian, right? Now, it's not hard to see that if I start expanding this representation so that actually I start connecting layers together and then having multiple neurons per layer, then I can actually get some really complex representations. And in fact, it is shown that a sufficiently complex artificial neural network can represent any arbitrary function to some given precision, which is to say that these models are universal function approximators. Right. Now that's really powerful because that means as long as there's a functional relationship between something and something else, say some input to some output, I can go ahead and represent that. And that's really useful. So that's sort of the groundwork for the background that we really care about. So let's talk about the work that we started doing, which is actually implementing something called a deep learning optimizer. Now, one of the things that I'm most interested in terms of my research is something called a quantum memory. So quantum memories are useful for a number of different quantum communication purposes. Why would you care about quantum communication? Well, that's a topic all on its own, but basically you can do some pretty neat things. You can do provably secure communication. You may be able to build interconnects between quantum computers, which is useful if you want to actually share information between quantum computers or have some sort of quantum computing cluster. And there's also other information processing tasks that you can do during communications in the memory. So what is a quantum memory? Well, generally what we're going to be doing is actually encoding information on states of light. Now, that's very useful because light flies around. It doesn't really interact with things if I don't want it to, which is very useful. So if I put my quantum information in here, I can get it from one place to another. The problem, of course, is that if I have a quantum memory, how do I actually store this light, right? I need to actually keep it, in one place for some time. I can't copy it because that goes against the laws of quantum mechanics. So I have to try and basically capture this light somehow. Now, if I gave you that task and I said, hey, take this light and put it in a box, keep it for later, and then at some other point I'm going to ask you to give it back to me, you'd be like, no, Aaron, that's stupid. I can't put light in a box. And you're absolutely right. But what I can do instead is I can replace my box with something that looks like an ensemble of atoms, right? And so that's sort of what we do with cold atoms. So the idea is, here's my lovely ensemble of rubidium-87 atoms, glowing nice and brightly here, to use what's called a magneto-optical trap. Now, I'm interested in using these for quantum memories, but for people who are in physics, you'll know these as being used for things like BECs, precision metrology, atomic clocks, all of that good stuff. Now, the thing that we care about the most is getting the most number of atoms in this trap that we can. The reason we care about that is that the coupling between the light and the atoms depends on the optical depth, which is really just a way, it's really just a quantity that's in some way related to atom number. Now, I care about this strength because if I don't have enough atoms in there, the efficiency of my quantum memory is going to go down. Right? I'm relying on there being more things in there for my light to interact with. And if I'm going to make a usable quantum memory, I need the efficiency to be quite high. Now, the process that we use to get these atoms into the trap is a process called laser cooling. Right? So you take thermal atoms, which are just sort of whizzing around in a cloud, and actually condense them by cooling them into the center of this trap. And to give you some context, these atoms might be on the order of like 60 degrees when they're whizzing around, and then by the time we cool them, we're actually hitting temperatures of hundreds of microkelvin, which is very cold indeed. So briefly, just a quick explanation of laser cooling, because that's going to be the main control knobs that I care about using here. Let's say I have some atom going at some velocity, and it's going to want to go in that direction without me doing anything. So what I can do then is apply a laser field in the opposite direction. And what that's going to do is, on average, if I set up the frequency of this just right, so that it's resonant with a particular atomic transition, it's going to absorb light preferentially from the direction that it's trying to go, which is kind of like the light pushing against the atom. So what that does is that when I absorb light from this direction, I get a kick in the opposite direction. And then I emit this light as spontaneous emission, but this light is emitted in any random direction, right? Which means on average, I have a viscous force which is pushing against me. Now I can be particularly tricky, and if I put beams in every direction, then no matter which way my atom tries to go, it always encounters this force pushing against it, and so I effectively cool it down. Now, this is the relationship between all of the parameters that I care about controlling and the various quantities. Now, suffice to say, we don't actually care about this in this context. This is really just to show that it is quite a complicated relationship between the things that I can control, which is things like the detuning from these particular transitions, and the magnetic field strength that I use to trap these atoms. The problem is, it gets even worse. I can't actually use any of this theory because I break all of the assumptions that I would normally use to actually trap these atoms, right? So I'm not in a low intensity regime. I'm not in a steady state. I have this strange geometry. So I can't actually use any of these things that I would normally like to use. And that's a bit of a problem. So just for people who are interested, I have something here called repump field detuning, which doesn't appear in these equations, but basically what it does is it actually makes sure that my atoms don't collect in a particular state by pumping them back out of that state, because otherwise if I just apply one field, they'd all end up here, and then I can't actually do my laser cooling. So one of the methods I can use to try and get more atoms in the trap is to use what's called a transient compression. So the way to think about that is if you imagine my atoms from before that are in this like elongated cloud, then what I want to do is over a period of time, basically try and compress them down as much as I can. The point of that is that when my light that I'm going to try and store for my quantum memory is going through this area of the trap, I basically want this to be as cold and dense as possible, because that's going to increase the efficiency of my quantum memory. So one of the ways I can do that is a technique known as transient compression, which has been around since about the 70s, and people have been doing it that kind of way since then. And the idea is to basically change these ramps in sort of a smoothish fashion to try and collect as many atoms in the trap. And so the idea is I ramp up my magnetic field so they get steeper and steeper. So basically my atoms get pushed closer and closer to the center of the trap. And then additionally, I also change the detuning of my fields such that I'm not scattering as much light and therefore I'm not losing as many atoms. So we wanted to come up with a new scheme, right? So if this is the old way of doing it, let's say I'm just going to take the most naive approach possible. So I'm going to give this 1 millisecond time controls because it happens over 20 milliseconds. And I'm going to do that over all three of those channels that I mentioned here, which means I'm now doing a 63-dimensional optimization, which is really hard to think about, right? If you try and imagine anything that has 63 dimensions, that's just not going to work for you. So we need a method to try and actually figure out how to operate this trap and how to actually optimize the behavior of our atoms. So what that means is that I'm going to have a bunch of experimental inputs, and I'm going to need to pass that into some model. That model is then going to tell me the predicted behavior of my system. Right? Now, the reason I've represented the model of the duck here is not because the model is an all-sentient, all-knowing duck, but actually because I don't really care what this model is, right? All I care about is that it represents this mapping in particular. And so that is the case technically with these atoms, right? I just showed you that I break all those assumptions, so my theory doesn't really make sense in the context that I want to use it in anyway. So I'd like to create a model that actually does this. So how do I make this model? Well, I can go back to what I already know and use something called a multi-layer perceptron, which is really just a fancy name for an artificial neural network. So it's actually going to provide this functional mapping between my experimental inputs and my predicted behavior. And even better, I don't have to care about the internals of that model. I can just learn it from the data. So what does that look like in practice? So what I am going to aim to do is set it up in a feedback type loop. And so we'll go through each of these things individually. So I start with my experimental loop, right? The idea here is that I'm going to implement a bunch of parameters on my experiment, which represents my various controls. After doing that, I'm going to end up with a nice cloud of atoms sitting in the center of my trap. Right? And how many atoms I have in there will depend on these control parameters. I then do some optical pumping, and the thing that I care about the most is the fact that I send through this probe beam. So this probe beam is resonant with a particular transition of rubidium-87, and depending on how many atoms are in the trap, it's going to get absorbed. Or it might just pass straight through if there's no atoms in there. So why is that important? Well, the thing that I need to train my neural networks is I need some sort of cost, right? And this cost is going to inform my networks how well I'm doing for a particular set of parameters. It's going to tell me how good my parameters are. So the way I construct this cost in this case is literally just the integral of the photodetector signal, which just corresponds to adding up how much light I get back out. So I can generate a bunch of training data by sampling all over the space and generating some random parameters. Now, I actually use 3 of these networks, and there's a reason for that. If I imagine that in one dimension I have sampled my function so that I have some system response for a given range of a particular input parameter, and normally obviously this would be multidimensional, but we can't think in multi-dimensions, so let's just do one parameter. Now the idea is that if I use multiple neural networks, I can actually get it to predict where a particular minimum will be in this landscape. But what's interesting is that where there's lots of data, they're going to tend to agree, but where there's no data, they're going to disagree about where the best point is. And that's really useful because now I can just go through and test all of these points individually. Eventually, if I had enough samples, I could represent this space perfectly and then I wouldn't have to worry about it. But usually with high dimensional spaces, I'm going to sit somewhere in the middle because it's really hard to sample things efficiently like that. So I then ask these neural networks after I finish training them, hey, now that you represent this landscape, tell me where the best point is. Tell me where the best set of parameters are that gives me the best cost. So I take these parameters and I can start to see trends and patterns between what's going on. Right. So here, this sort of purpley color corresponds to having the most atoms in my system. And along the x-axis here is actually the time value pairs of my particular trapping scheme. So there's 21 points across here, so 3 channels makes you 63. And you can see that I start to notice these particular trends. So for example, in here, it doesn't really matter which value I pass through in this area. I can go through anything and I'll get a good cost. Whereas over here, I really need to be going through this point if I'm going to do well at all. So all of these parameters start to get fed back to my experimental controls. So they basically come back into my experiment, I implement them on the experiment, and I do the same thing. I measure a cost for these new parameters, and then I'm going to take this cost and parameter pair, add it to my training set, retrain my networks, ask for a new minimum, and just keep going around and around, and around in a loop. Now, the point of this is that I just keep doing this until I reach some sort of convergence criteria. So how well does that work? Turns out it works pretty well. So I have initial training bit here, which is basically just trying sort of random parameters to get an idea of the landscape. This is like, you could think of this as building up an initial knowledge, right? So if you have some landscape that you're trying to walk around, kind of like a map in real life, you need like some points to at least figure out maybe where you are. And then after that, I kick in my optimization, and you can see it pretty rapidly converges on this relatively good cost. So what does that look like experimentally? Well, I generate something that looks completely crazy. And this is a solution that no experimentalist would ever come up with because it looks like it's insane. Right, and let's compare that to the original thing that people have been doing from the 70s, and there is really just no similarities, right? It is turning these things off, on and off really fast and really hard. It's going to hit each of the rail boundaries, and it's going to do that in something that doesn't even look like a pattern. And this is crazy, right? If someone gave this to me as an experimentalist, I'd be like, what is this? Did a child draw this? This doesn't make any sense. So the question then is, well, how well does it do? Well, it turns out it does quite well. So what we can do is we can take images from the side of my atoms. So what this corresponds to is I have some atoms in my trap, I'm sending through some light, and I measure how much of that gets absorbed, and that is basically imaging my atoms. So here you can see the human version of the transient compression. This is those nice smooth ramps that I had before. So they start off nice and fat, and then they slowly compress down until I have this thick ensemble. In contrast, if I look at the machine learned solution, which for some reason isn't playing, basically what you would normally see is it starts compressing, and then it opens up again, and then compresses, and then opens up, and it does this sort of double compression scheme. Now, these images on the left-hand side here, they aren't calibrated for the atomic density, but we can look at these images on the right-hand side, which are actually calibrated for atomic density. And so you can see the machine learned solution has got a lot more atoms in this area. And so this is the transmission plot if you take the integral in this box. Now that corresponds to a optical depth increase of 530 to 970, which is about 86%, which is a really hard increase in atom number to try and do as an experimentalist on your own. Right, that's a lot of time, and especially trying to come up with a solution that looks as crazy as that previous one. That is something that we would never have changed. Now, interestingly, what this method looks like it converges to is something that is used in the optical lattice community called release and recapture, where they actually have these optical lattice trapping sites, and to increase the occupancy, they basically release the atoms and then try and recapture them. Release them and then try and recapture them. An analogy that we came up with to try and explain this is if you imagine you have a box full of packing peanuts and stuff in there doesn't fit really well, and then eventually you just kind of shake the box and everything just kind of settles and fits in where it should, and fills all the gaps. It's a little bit similar to that. So let's move on to the final part of this talk, which is other deep learning applications. So the interesting thing about the deep learning optimizer is that it really doesn't care what you apply it to. So we applied it to cold atoms for quantum memories, but you could just as easily apply it to anything else. And actually that's what we set out to try and do, because we want to know, well, where does this thing stop working? And the answer shortly is that we really haven't found something that doesn't work on yet. So for those who aren't familiar with it, anyone who's worked with optics will have come across at some point in their life an optical cavity. So we wanted to know if we could do what's called an auto-alignment. Now, let's say I have some mirror, and I have incident on this mirror some light. Now, it's a pretty good mirror, so most of this light is actually just going to get reflected. But some of it will actually leak through the mirror and actually be transmitted, because no mirror is perfect. Well, what happens if I put a second mirror here? Effectively, that little bit of light that gets through is going to get stuck in between these two mirrors and go round and round and round, building up a fairly large amount of power inside the cavity. So what I can then do is look at the transmission of this cavity, because some light will still escape, and use this as sort of a filter. So what I can do is, if I look at moving the position of this mirror, I'm actually going to constructively and destructively interfere the paths that this light is taking inside this cavity. And that's going to correspond to filtering out particular things that I don't want. Now what I can do is, if I take a camera and look at the modes of this cavity, then what I find is something that looks like a spatial mode. And so this spatial mode is going to be dependent on the location of this mirror. Right? So sometimes I'll find modes that look like these circular Gaussians. Other times I'm going to find modes that look like two lobes. Sometimes I'm going to find things that look like donuts. Sometimes they look like jam donuts because they got a filling. Now, the important thing about that is that to basically get the mode that I want, to choose one of these in particular, I have to very carefully align this cavity. And it requires quite a bit of tuning and quite a bit of alignment. So the idea would be to do this automatically, so that I don't have to do this every time, because sometimes this needs to happen on a daily basis. Now I will point out a caveat that someone pointed out to me, is that to do this you actually have to give control of lasers over to some machines. I haven't figured out if that's a good idea yet, but I don't think they're sentient, so I think we're doing okay. So this is what the actual experiment looks like. Now there's a little bit going on here, but the main things that we care about are these 6 actuators. So I have some mechanical actuators which just look like little screws, and they basically move things back and forward. Now I can put 2 of these on the lenses here, which are part of my beam expander, and if I move those around, what I'm effectively doing is, if I have some laser beam going through these lenses, I'm basically expanding and contracting this laser beam. Additionally, I have 2 actuators per mirror on each of these steering mirrors. And what that allows me to do is actually point the beam in different directions and also translate the beam in different directions by moving these relative to each other. So using all 6 degrees of freedom, I can couple into this cavity here nice and easily. Now that's really good, but how do I figure out how well I'm doing? As before, I need some sort of cost function. So the way I do that is I look at the transmission of this cavity on a photodetector. And this transmission is going to look like a bunch of peaks, and each of these peaks will correspond to one of these spatial modes that I saw before. The idea is that when my cavity is properly aligned, I should be able to take the peak that I want, which might be, for example, this one here, and transition to a regime where I only have this peak and I've suppressed all the other modes. Right? And so this would be the ideal case. I start with something like this, and I end up with a nice spectrum like this. So how well do I do? Well, we have some preliminary results on this. So here we can see that we have our initial sampling, which is set up to be about 50 runs. And so this is the same as before. It's trying all different random positions of these controls. And then within 200 to 300 runs, we've already basically reached the maximum that we could find for this particular system. So we're quite efficient at getting there. So these traces here actually correspond to the positions of the mirrors. And so you can see that initially we start in some kind of okay configuration, and eventually by the time we get to 200 to 300 runs, we've converged on the final position of the mirrors, and that's where we should be. Now these spikes here correspond to the neural network trying different parameters, because it's always going to keep trying to explore, because you never know if you're really in the best spot or if you're just close to something. So you might as well just keep trying for as many times as you can. Now I talked about wanting to have a single peak in the trace before, and so we can actually look at this, and this is the output that we get, which is looking pretty good. It should be noted that we have this little peak here, and unfortunately this is limited by the input purity. So the beam that we're sending into this cavity has some astigmatism. It's got a little bit of ellipticity, and so unfortunately we actually can't get rid of that. The machine learner doesn't have control over this astigmatism, so it can't get rid of it either. It can just do the best that it can to try and put as much power as possible in this particular mode. Now, it should be said that you can actually use the same approach for many different optical systems. For example, LIGO, who's done the gravitational wave detection, they have auto-alignment principles that they need as well as things that are based in space for communications. So the final thing I want to talk about today is machine learning for silicon quantum computers, which is some work that I've been doing with UNSW as a collaboration. So I'm not sure if anyone's aware, but quantum computing is kind of a big topic at the moment. And one of the approaches that's been pioneered in Australia is the use of silicon qubits. Now, the point of using silicon as a platform is that once you get this kind of stuff working, you can leverage the entire semiconductor industry. And that's very useful for scale-up. The problem at the moment is that fabricating these devices is still actually kind of a challenging endeavor, right? And you know, if you ever looked into it, you probably see nice pictures like this. In general, the pictures that I receive look a bit more like this. So this is a 2-qubit device that was fabricated at UNSW, and so this is imaged using a technique called scanning tunneling microscopy. Now, the bit that we particularly care about are these qubits here. So these are patterned into the device using the STM, and in particular, what we want to know is how many donor atoms are present in each of these qubits. And we need to be able to do that quickly if we're going to scale any kind of fabrication method, right? At present, it currently takes on the order of months to figure out how many atoms we're going to have at each of these sites. So that's obviously too long. We should be able to do better than that. But the question becomes, can we use ML to speed up this process? And this wouldn't be a very good talk if I said no. So obviously the answer is we probably can. Let's try and use convolutional neural networks. So what are convolutional neural networks? Well, they are a particular type of network architecture that has demonstrable success with image processing tasks. So anytime you've seen something that can take an image and identify what's in the image or what the image is doing, figuring out bounding boxes, that kind of stuff, is probably likely using a convolutional neural network. So how do they work? Well, let's start with an original image. We are all familiar through some form or another with the abundance of image apps these days with something called a filter. Now these filters can do lots of different things, but sometimes you can actually use them to do really useful things. Now the idea is that this filter is applied to a subset of the image, and it moves across the image while I'm applying this filter. And when I do that, I can actually filter this image. Now, this is a little bit hard to see, so let's zoom into a particular region. What we can see here is that this particular filter is performing an edge detection. Right? I can see the edges of my house here, the edge of my roof, compared to the background. So the background is a flat color, so it's basically got no information for edges, but this is the information that I'm getting out. Now, why is that important? Well, if I give you a picture of a house, one of the ways that you can tell that the house is in here is by being able to distinguish it from the background, right? As well as the shape of the house. If I were to make the house the same color as the background and then start to blur the edges, it's going to be a lot harder to tell that there's a house in there. So there's obviously something to do with the edges and the sharp boundaries of this house that allows you to so easily identify that there is a house in here. And then there's also things like color values, right? I expect that the sky is probably not red. This looks like it's probably taken somewhere in rainy Europe or Canberra at the moment. So, you know, we can usually distinguish what's sky, what's ground. So there's information in multiple different channels of these images. And we can use filters to get that out. So the question then becomes, well, how do we design these filters? And hopefully I've got across the point that we don't bother to design these, we learn these filters, because that's going to be a lot easier. So the problem that we have with this particular data set is that while we can pull out each of these qubit sites automatically, by the time we do that for all of the devices, we only have about 30 of them. And that's just simply because making these devices is actually quite difficult. It takes a lot of time, it takes a lot of manpower, and then characterizing them and knowing exactly what's in there so that we can use them for training is a hard problem. So what can we do about that? Well, we can use something called objective invariant transformations, which is a big fancy word for doing things to the image that doesn't destroy the information. So two of those such things are translations and rotations. So for example, if I give you a picture of a dog and then I move the dog around in that image, you still know it's a dog. It doesn't change the information. Similarly, if I turn a dog upside down, the dog doesn't suddenly become a car, it's still a dog. So I can do all of these things and use that to extend my training set so that I now have a much larger set of devices to train off, and so I can extend this from 30 to more like 3,000, which is a number that I can start to work with. So how well does it work? These are some preliminary results for what we've been working on, and this is what's called a confusion matrix. So basically you have the truth on the top left here, and so we basically have at a particular qubit site what the donor number should be. So at site 1 we have 0, 1, 2, and 3. So we're interested in predicting up to 3 at the moment. Now I can look at my validation accuracy, which is basically some secret data that I keep away from the model that it's not allowed to see, and so this never appears in the training set. It's sort of like asking it to predict it afterwards. So it's kind of like I give you some information and then afterwards I'm going to test you on some unknown information that you can probably generalize from the information that I've just gave you, right? Then additionally, we also have some tests accuracy, which is a little bit more esoteric here, but basically what it means is that this data is not even used to stop the model in terms of its validation. And then we have an ensemble accuracy, which is just an improvement over the test accuracy. And the way we do that is just by creating an ensemble of these models and asking them to predict and then sort of looking at their average predictions. And that's kind of like having a group of experts instead of one. Now, if you look at the accuracy of these models, you can see that we vastly outperform the expert accuracy. For this particular data set, you would expect that if you just picked one particular device, the best you can expect to do is about 44%. So if you were just picking randomly, you would or if you just picked a particular device as your strategy, the best you could do is 44%. And so the models are actually outperforming the experts by quite a bit. We can get validation accuracies on the order of 90% depending on the data set. So we can also do something interesting here, which is look at how the machine sees the world. Now I've got two layers here, which is the before and after dosing. I haven't talked about the after dosing, so let's just ignore that for the moment. But this is the actual structure of the model. So we have our input, our convolutional layers here, some pooling, which is just subsampling, before finally going into our classification layer. Now the thing I want to draw your attention to is this particular area here. Now what's cool about this is that without any input from us, the neural network has kind of learned to do edge detection, because if you are looking at the size of things, which we think should be the best predictor of how many atoms we expect to find in there, after dosing, then we should just be looking at the size of this by looking at the edges, right? And it looks like the network sort of figured out how to do that on its own, which means it's actually got, hopefully, some physical ties back to reality. And that's super cool. So I'd like to finish up there. So just to put a summary up of what I've talked about so far. So machine learning, I hope I've gotten across the point, is a powerful tool for physics, but also for science in general. You know, we see lots of applications in industry, and obviously people are embracing it because it does work. But there's also a lot of really interesting stuff that you can learn by putting it in a science context. These approaches generalize to learning complex physics. So we've seen with the cold atoms that it can figure out, these new trapping schemes that we haven't seen before. We've also been able to show that, it can work with systems that are entirely different. So for example, the cavities, and finally the ability to pick out those atomic structures. And finally, there's still many unexplored applications. There's a lot of stuff that you can throw these models at. You have to be a little bit careful. You can't just go willy-nilly and throw them at anything you want. You will just, the old adage, garbage in, garbage out. But there's still a lot of interesting stuff to explore, and we're going to keep doing research on that over the next few years. So if you've got any interesting problems that you want to come and talk to me about, feel free to. I always love to have a chat. And with that, I'd just like to acknowledge some people. So everyone from the Cold Atoms team, the Auto Alignment team, my collaborators at OIST, and also my collaborators at UNSW. And once again, thanks to the organizers for inviting me to give this talk.